So that was the first major branch of research in deep learning for object detection that relied on extracting regions and region proposals to do the detection. The main issue that is left to be tackled is if it's possible to remove now this proposal stage and do detection in the same way that we do classification. So with one pass of a network, predict all the bounding boxes and class scores from the convolutional feature maps. So we don't want any feature resampling stage and remove the proposals. Essentially, what we want to avoid is to have to perform multiple classifications on multiple proposals. So we want to eliminate the region proposal step. And this will help also in real-time applications while maintaining the accuracy of region proposal methods. So the basic structure, as you see on the figure, of a single shot, as we call it, detection approach is to have a backbone network. Usually it's pre-trained on ImageNet to act as a feature extractor. And then we add some additional layers on top of that to process and facilitate the predictions of the bounding boxes. We have a spatial association between what is in the output and what is the, with respect to the input image, as we will see. One of the first algorithms for single shot detection was YOLO. It stands for You Only Look Once. And it's an algorithm for single shot detection that predicts bounding box along with the classes of each object with a single pass from a convolutional neural network. And the idea is to split the image into grids and predict bounding boxes for each in each grid. They predict an objectless score similarly to how the region's proposal networks worked, and they multiply that with the classification score to determine if an object exists or not. This is the overview of their approach. So let's go now and see these steps in a bit more detail. So we start with an image of a predetermined size. So for ImageNet, this is 224 by 224. Some later works used larger images. In any case, what we do is split this image into a grid of cells. Each grid has a size that is the factor of the image size. And the idea is to have objects centered at each grid cell, so that grid cell can predict that object that is centered at that location. So each grid cell predicts the probability that an object is centered at that location and the potential class of that object. So two things, the objectness and the classification. It also predicts a bounding box enclosing that object. Typically, it could also predict more than one box, and we will see how. And all grid points predict bounding boxes. As you see in the visualization, we have bounding boxes all over the image, but the objectness score, which is the confidence that there is an actual object in that area, which is visualized here by the thickness of the of the box allows us to basically remove what has low confidence. Additionally, each cell predicts an object class. So here the color of each cell indicates the class that it predicts. So you see some areas near the car are predicting car, some areas near the dog predict dog, and some areas basically predict something that might not be there. So for example, the grid points near the road may not have any object there, but predict something that might be more prominent in the car class. So the important thing here is that no matter what, there's always some class prediction coming out from each of these cells. If we now go and associate each of these boxes with the predicted class, we get at the same time the color of the box that indicates the class, the thickness of the box that indicates the confidence in having an object, and this gives us, in essence, the whole prediction of the network. Then what usually happens is that we have to post-process all these predictions to make sense and remove noise. So basically, we do some thresholding, and we apply an approach, a method called non-maximum suppression. We first threshold each box by multiplying the class score with the objectness score, the confidence that there is an object. And this has to be over a threshold, usually 0.5. And the remaining boxes that have a high confidence and high class score, we apply non-maximum suppression. So we only keep amongst a group of overlapping boxes, we only keep the one that has the highest score, as you see in the figure with the car. And this basically cleans up all the noisy detections. So putting everything together with the YOLO framework, we simultaneously predict boxes, classes, and objectness with the same convolutional neural network in a single pass. And the key here that allows this to work is the association between the input image and the grid, and the grid cell. So this encoding that we do that contains all the object information. In this initial work, it's called YOLOv1, because there are other versions coming up later. They use the convolutional network similar to VGG, so some convolutional feature maps with 77 kernels, some fully connected layers, and then some restructuring of the output to make it into a 3D feature map to help in the decoding phase. And as you can see, for the Pascal VOC dataset, the output is a 7x7x30 tensor, and 7x7 basically means they have a 7x7 a grid cell, and they and for each one they predict 30 values. So these 30 values is how they encode the object information for each of the boxes. So for each grid cell, they predict the probability of an object, the bounding box coordinates, and the probability of each of these classes. And this essentially means that for every grid cell, they have one bounding box prediction. If we want to increase the number of bounding boxes that we want to predict, what we do is we replicate this this tensor and stack it together, and this basically increases the number of boxes we can predict. In the first version of YOLO, they predicted 2 bounding boxes. So essentially, they had 2 of these tensors stacked multiple times. And this is the objective function that they used to train the network. So it might seem intimidating at the beginning compared with, for example, the previous region proposal network, but it makes sense. So as you can see, the first 2 terms basically regress the coordinates of the bounding box. So the center coordinates x and y, and the box width and height. And notice there that they have this square root for each for the width and the height. And the reason for that is that they want to avoid, when you have small numbers, so small windows, small boxes, small deviations in the don't produce a high increase. So by square rooting the small numbers, they make them larger, and so the signal is stronger for propagating the gradient. So next, they regress the confidence score for object locations and non-object locations. So the idea here is in the grid cells that there is an object, they want to predict the presence of an object, and in all other cases, which is the second line of the 2, basically for those boxes, they propagate the non-object class. And finally, they regress the classification using squared error to predict which of the classes the box belongs to. So at training time, we only want 1 bounding box for each object, and this is achieved by having this matrix of binary values for each cell, where we assign it to 1 if the ground truth corresponds to an object being assigned at that particular grid cell. And it's usually set at 1 for the predictor that has the highest IOU with that corresponding cell. We also talked that the reasoning behind the square roots to avoid having small deviations to matter less. And also for the confidence values for object and non-objects. So the important thing here is that they have this constant, the lambda constants, and they basically control how much of information is propagated from the loss. And because usually in a detection framework, we have many more negative examples, so non-object class, non-object areas than object areas, they put this lambda to have, they set this value to have a small value, in this case 0.5, so that they suppress the information coming from the majority of the negative classes. So the first version of YOLO managed to to achieve its main objective, which was to speed up the process with respect to region proposal methods. It achieved 7 times faster performance than Faster-RCNN, but if you look at the accuracy, it was lower. This was mainly due because it predicted only 2 bounding boxes at every grid cell, and this limited the number of nearby objects that it could predict. So most of these errors and the drop in accuracy happens because of the bad localization. But still, the detection accuracy is high compared also to previous methods. And there is a significant, as you can see, order of magnitude speed up in terms of frame rate. Not surprisingly then, the same group worked on an improved version of YOLO, the version 2 YOLO, and they tried to further improve their initial work with regards to accuracy and speed. So they proposed improvements over the first version with regards to the underlying network they use and the way the predictions are made. They also proposed what is called the YOLO 9000, which is a way of expanding the number of labels that the network can predict by combining it with classification labels, which usually have many more classes. And as you can see, they managed to push the envelope in terms of both accuracy and speed. The main improvements with regards to the YOLO v1 version were that they increased the classifier complexity, so they developed their own custom network, and they trained that network using multiple resolutions, which helped in trying to finding objects at different scales. In addition, they removed the dense layers and replaced them with convolutional layers, which helped in reducing the number of parameters. And they used techniques such as batch normalization to help with accuracy. Another thing that they worked on was to improve the localization performance compared to the first version. So the main problem with the first version was that it did not have constraints on the location of the prediction of the bounding boxes. What this means is that a cell at the upper left corner could predict an object at the bottom right corner. So there was no spatial constraint on what is being predicted. And so a major change with regards to the first version was that the location was now bounded and fixed at each cell. So a cell could only predict objects in its own area that it was responsible for. So a bounding box remains within the grid cell. Another improvement was with regards to the number of boxes per grid cell. They used the concept of anchor boxes that we saw before with region proposal methods to set some predetermined aspect ratios and scales. So basically, they used the k-means clustering algorithm to identify what are the most common aspect ratios and scales of bounding boxes in the VOC class, and they used those as anchors for setting up their prediction. So they don't predict actually bounding boxes with respect to the input image, but they predict some offsets with respect to these anchor boxes that they extracted from the k-means. And in the images here, you can see some prototypical anchor boxes that can be used. And all grid boxes have the same exactly anchor boxes as the templates. Now, for each grid cell, they compute an offset from its top left corner. This is to find the XY, the center of the bounding box, which is bounded by the bottom right corner of the cell. So they use the sigmoid function to basically for each of these coordinates to find where in the cell it's located. And the width and the height are predicted as scale factors on the anchor box using the exponential function. So they this helped them to increase the effective range that they could work with. So overall, this parameterization and this mapping with the anchor boxes allows direct prediction of all the bounding box information in a single pass. Another important aspect introduced in YOLO version 2 is a custom convolutional feature extractor. They proposed a convolutional network that we refer to as Darknet-19 as a replacement for the network that they used before, for example, a VDG or a GoogleNet. And the network is pre-trained on ImageNet, and it mostly uses 3x3 filters with some 1x1 filters to reduce the parameter size and compress the feature representation. In total, it had 19 convolutional layers, that's why the naming, and 5 max pooling layers to reduce the data spatial dimensions. And it achieved a similar accuracy to ResNet and VGG, but with less computational cost. This is on ImageNet. So similarly to the first version of YOLO, we interpret the output feature map as a grid of cells. In the case of YOLO v2, it was 13 by 13 because they also doubled the size of the input image, so the grid cell doubled as well. And this allows them to predict more boxes overall. So each cell in the grid has 5 independent object detectors. So each tensor that we stack up is essentially a different detector. And the key thing here is the position of a detector is fixed. So it can only detect objects located in that particular cell. Each one predicts a single bounding box, like with a regular classifier, it predicts a number of classes using a classification metric, and we get the maximum of these classes to assign to the bounding box. So the model always predicts the same number of bounding boxes, which sums up to be 845. And obviously, the vast majority of these predictions will belong to the negative classes, so background, essentially. And the confidence score together with the objectness can give us the predicted boxes we can ignore. So the training of YOLO v2 had 2 phases. First, they had to train their backbone Darknet-19 using ImageNet to learn useful features, and then fine-tune that on larger images, again for classification, and then move again the same process for detection. So fine-tuning the network for detection this time. and they also used some different learning rates to improve convergence. So as you can see here, from YOLO v1 to YOLO v2, there is a clear progression with the additional improvements. And the main contribution, it seems, that pushed accuracy higher were the higher resolution classifier and the batch normalization also at the beginning. And the improved localization capability through the anchors and the constraint of the prediction of the location prediction of each grid cell also improved significantly the accuracy. So overall, it was more than 10% accuracy improvement from the previous version. But one challenge that remained for the YOLO v2 was with respect to detecting smaller objects. So it had difficulty in detecting objects with small bounding boxes. And this brings us to the latest version of YOLO v3 that tried to primarily boost the accuracy, especially with regards to smaller objects. And let's see now some of the main ideas that they introduced in this paper, which was not published in a conference, but it was more published online in a repository. So in general, they worked a lot on the network. They used a much more complex network with many more layers. They use what they refer as a Darknet 53. It has 53 convolutional layers now rather than 19. They introduced some shortcut connections to connect earlier layers with deeper layers, and they removed the softmax function so that they could and replaced it basically with sigmoids, so they could now predict multiple labels for each object. But perhaps the major contribution is came in the form of a multi-scale prediction from different parts of the network. So before they had at the output of the network only one tensor with stacked predictors. Now they had multiple outputs from the network coming from different parts of the network. And this is also what we call a feature pyramid network. The idea here is that we make predictions at multiple feature maps that could be at multiple scales. So specifically here, they used different number of grid cells for each output. So they also assigned different anchors to each of these outputs. And they combined the loss of the outputs to train the network end-to-end. And this basically makes it much better at detecting smaller objects than YOLO v2. And it also predicts many more regions than YOLO v2. And basically, the detections at the different layers is what helps to address the issue of detecting small objects. And the idea is that the higher resolution maps, basically, early at the network, we can find smaller objects, and as we move in, we can detect larger objects. And for this, they also increased the number of anchor boxes from 5 to 9. And they assigned 3 anchor boxes at each scale. They arranged the anchor boxes in descending order, starting from the largest ones. And they assigned the first 3 to the first output, then the second, and so on. And this allows them basically to make more specialized detectors for different scales. So comparing the YOLO family with the RCNN family of networks, we can see that YOLO managed eventually to catch up to the accuracies of fast and faster RCNN with some reduction in speed, as we can see. And this is the major difference between these two families. So depending on if you are looking at real-time performance, you could shift towards YOLO or single-shot methods in general. If you are looking for accuracy, you don't care that much about when you get your result, and maybe Faster-RCNN is a more a better solution for that task. Next up, we have a single-shot detection framework, which, as the name suggests, is another approach for single-shot detection. It is similar to YOLO, as it again simultaneously predicts the bounding boxes and class probabilities. But it formulates the detection task a bit differently, and it has a different convolutional network and a different architecture. Specifically, the main difference, especially with the earliest version of YOLO, was that it uses maps, different feature maps from the convolutional network to make predictions at different positions. So again, it uses this idea of a grid cell, and each of these boxes again predicts 4 parameters, as in YOLO: the coordinates, the center, the width, and the height. But the major difference is that they don't have an objectless score, but rather they treat the background as another class in their instead of having 20 classes, they have 20 plus 1 for the background. And for this reason, there are different challenges during training when dealing with negative examples. Since now we have an imbalanced classification problem to deal with, so we have to treat it with different training strategies. So at training time, we again match the default anchor boxes with the ground truth boxes based on the IOU. For example, here we matched this, the red and blue, with the ground truth boxes. And so we update those boxes with a location, and we treat the others as negative examples. So we update them as they were. They did not contain any object. So because of the difference between these with the objectness and that YOLO has, and the fact that SSD uses treats background as another class, their loss functions also differ. So the SSD loss is a weighted sum between the localization loss, the smooth L1 loss that we had also in the region proposal methods, and the classification loss, which is based on cross-entropy. Similarly to YOLO, it uses the IOU to mark the boxes as negative or positive based on the threshold. And you can see that it transforms each of the ground truth box with respect to the default boxes. So essentially what this means is that our network predicts these offsets and these scaling factors with respect to the default boxes. So the major difference between SSD and YOLO v1 and YOLO v2 at the time was that they add much more convolutional auxiliary convolutional layers. So after the VGG, they add more convolutional layers, out of which they make predictions. And basically, this means that they predict boxes at different sizes from different convolutional maps. And at each level of these convolutional maps, they have their own predictors, so independent predictors that learn the particular features of that scale. And there's no transfer of features between the different resolutions. So there's no high-level context moving into lower-level feature maps. And in 3 of these layers, they make 6 predictions, so 6 bounding boxes in per grid cell, and in the others they make 4. So in total, they have over 8,000 predictions for these 6 layers. So as we see here, the multi-scale feature maps, the fact they have so many, predict so many bounding boxes from different scales, helps a lot in reaching high accuracies. Note here that the input resolution is different between the different approaches, which also plays a role in both the speed and the accuracy. And we can also see that at the bottom table that the accuracy with respect to the additional scales is improving considerably. So it helps to have multi-scale prediction, and it also outperforms other methods as well as the first version of YOLO. However, the latest version of YOLO manages to reach these high accuracies, as it also has its own multi-scale prediction. So comparing the different single-shot, the most prominent single-shot approaches, the main differences, especially between YOLO and SSD, is that we started with YOLO v2 that had a single output, then SSD came in with multi-scale prediction, and then YOLO v3 catched up and also added its own version of this multi-scale prediction. So overall, they have differences in the way they predict their outputs. So the objectness score, which is not present in SSD, the loss functions are different, but the most recent versions look more and more similar. Okay, this ends the 2 major approaches that I use today in single shots, so YOLO and SSD. And we'll talk briefly now about some other works that try to address some similar problems in different ways. And also they added into the development of towards more accurate single-shot detection with deep learning. So the first is a series of ideas that came up in the feature pyramid networks paper that basically tried to address the problem of detecting small objects. And the main observation that they wanted to exploit was that the deeper layers in a convolutional neural network usually contain a high level of semantic information, but they are at a low resolution. On the other hand, the early layers are of high resolution but have more structure of the object rather than semantic information. And the thinking behind this paper was, can we just somehow try and merge these two together? And the idea they proposed is to start from the end of the network and upsample, basically increase the spatial resolution of the semantic map, and add it from and add it to a previous layer which has the same resolution, so that they combine basically contextual information with semantic information. So they keep upscaling this map again, and they add another higher resolution layer, and they do this for at a few levels, and then they make predictions of bounding boxes at each of these combined feature maps. So in contrast to SSD, which only uses the lower convolutional layers for detection, here we have a much more structural way of incorporating high resolution information. So a follow-up to that, and from some of the same authors, was a paper called, a network called RetinaNet, which basically tried to address a major challenge for any detection system, the fact that we have more number of negative examples and negative samples than positive samples. So YOLO addresses this by weighing less the non-object grid cells using the weight. SSD has a selection process to manage the number of negative and positive samples. And in this paper, they propose something different, something more elegant. So they do this with proposing a loss function called focal loss. And the idea behind focal loss is to basically suppress the loss signal that is coming from well-classified samples, so that the network training and optimization can focus more on samples that are not well classified. So, for example, we have negative examples that are well classified that should not impact the loss function. So we suppress those information coming from them, so that the optimization can focus on the samples that are not well classified. And this is essentially how the focal loss operates. You see the effect in this graph right here. So they added, compared to the cross-entropy loss, they added a factor that is controlled by focusing parameter gamma. And the effect that this value has is that as we increase it, basically, as we increase it, what it does, it pushes the high samples with high probability pushes their value downwards. So increasing this gamma value essentially makes it so the value of well-classified samples is suppressed. So when an example is misclassified and its probability is small, then this the modulating factor here, the multiplicative factor is near 1, and the loss is basically unaffected. As this probability goes towards 1, so a sample is misclassified with a higher probability, then the factor goes to 0. And so the loss for well-classified samples is downweighted. So when this gamma is 0, basically this reverts back to cross-entropy loss. So as you can see on the graph here, for well-classified examples, for gamma equals 0, we have the top curve. And as gamma increases, then the value goes down. So we only remain with examples that are not classified confidently, let's say. And this can help the optimization to focus more on those samples. But as I said, YOLO, for example, has a different mechanism for dealing with this using this objectless score. And if you look at the loss function, essentially the weight that controls the objectness, it does essentially this the similar thing. So it suppresses the loss value coming from negative samples. So you see here that the one-stage RetinaNet detector with the focal loss outperforms all previous works on the COCO dataset this time, including the best reported Faster-RCNN method. But if you look at the YOLO v3, it's close in terms of accuracy, but is much faster in terms of speed. So if we want to make RetinaNet, for example, as fast as YOLO, then we have to sacrifice some significant accuracy to do that. So you can see here the different trade-offs that are in play and the different choices we can make when choosing a detector. So lastly, there are some lines of work that propose the idea of training object detectors from scratch without having to first using ImageNet to pre-train a feature extractor. And this is important because we want to build a custom detection convolutional network, and it may not be feasible to train again on ImageNet. Also, in many cases, ImageNet may not represent the actual target task that we want to perform. So there's been some line of works recently that try to make devise some strategy and some modifications in terms of the architecture of the convolutional network so that it's possible to train a detector from scratch on the target task without having to go through the process of training in ImageNet. And this particular one of the things that they suggest and they propose in their strategy is to use what we call densely connected layers. So the idea of densely connected layers is that we take the earlier layers and we propagate them back to deeper layers. So there is this connectivity pattern where every high level leads to better flow of gradients into the early layers. So it enables signal from the gradients to reach these starting layers. And this makes it possible to train a network from scratch without having to go through the ImageNet's pre-training. So as you can see, the results here are quite close to what other methods with pre-training have used. Of course, we're not there yet, but there's some line of work that goes through this direction. So as we saw, deep learning, due to its powerful ability and advantages in dealing with challenging image data, has become a major component in modern object detection systems. We saw the different families and how we first started with the traditional sliding window approaches, and then starting to move towards region-based methods to make more intelligent selection of the regions we want to process. Then we saw how we moved away from that into trying to make the detection task more similar to a classification task with a single pass of the image through the network, and how over time these single shot methods became better and better. And now the recent developments in architecture and loss functions allows us to have comparable performance with region-based methods.